Okay, let's continue with Riemann mapping theorem. Okay, so what did we learn so far? We learned that given a proper simply connected omega, there exists a conformal map. So conformal is conf dot g from omega into omega tilde, such that g of our initially chosen point z0 goes to 0, and omega tilde is contained within the unit disk, like this. So this is simply a way to reduce the problem down to a bounded set that sends our initial point down to 0, and now we're going to be considering conformal mappings from this guy that actually fix 0. Right? And we're going to try and find one that maps this guy, which is a subset of the disk. So this is our guy omega, and it contains 0. We're trying to find some conformal map that maps this completely onto the disk. Okay? And that fixes 0, and that sends 0 to 0. Because if we do this, then by composing such a mapping, let's call it F, composing F with our capital G will produce a conformal mapping sending our original domain completely onto the unit disk. And that's the statement of Riemann's theorem, and it'll have the property that the composed mapping will send Z0 to 0. Okay? So if we find such a mapping F that sends this to the entire disk, such a conformal mapping, and f of 0 is 0, we're all set. Okay? But we have to build up to this task. So what did we do? We also established that if we consider the class of functions f, which are holomorphic mappings from this subset omega into the unit disk that are injective, that fix 0, and of course holomorphic, then we let S be the supremum of, say, g prime of 0 for all g belonging to this family of functions f. And what we showed was that there exists some f inside our family such that this guy actually achieves the supremum. Okay? That's where we were at the end of the last class. So now we want to go from this to establish that actually this f that does this thing that achieves the supremum has this property that maps this omega tilde onto the entire disk. Okay? Which is kind of surprising, but that turns out to be true. And let's see why that happens. So, proof continued. So we're going to argue by contradiction. And assume that's false. So there is some P which is inside the disk, which is not inside the image of f of omega tilde. So let's draw a picture of what happens if this is not actually true. So if this is not actually true, then the image of omega tilde under f is not the entire disk. Say it's something like this, and there exists some P here, which is actually not inside the image of f of omega tilde. So there exists P belonging to the disk, but not inside the image of f of omega tilde, like this. Okay, cool. Okay, so we're gonna do a sequence of things we're gonna create a sequence of maps that changes things around. So I can't find better words than that. So let's start with the following. So we recall guys like this, these diffeomorphisms of the disk, which are like this: p minus z over 1 minus p power of z. Right? So these are diffeomorphisms of the disk. We showed this. We know that p of 0 is equal to p, and Tp of p is equal to 0. So these guys just essentially swap 0 and p. Okay? They're automorphisms of the disk where the role of 0 and p is swapped. So we're going to take this guy and we're going to consider the mapping which does this, that consider T of p composed with f. Okay? So what will that do? So your first mapping is to take omega tilde, map it into the unit disk, missing out p, and then we're going to take this mapping T of p, whose role is to put p into the center. Okay, so then the image of f of omega tilde under T of p would look something like this. It's going to now be something. It's still going to be simply connected, of course, because these are all diffeomorphisms. But now it's missing out 0. So this is what we've got, right? And then this thing is T of p of f of omega tilde, like this. Okay? Cool. So let's write that down. So this guy applied to omega tilde is simply connected. And 0 does not belong to this set. Okay, 0 does not belong to it simply. No? So this being the case, we now are in a position to define a square root on this set. As we discussed before, the square root depends on the set. This set might be worse than this. It might be spiraling round and round and round, but it'll still be simply connected. So we can still define an angle function on this. We can define an argument on this, which is continuous, okay, and which is such that when we define the log, then that thing will be perfectly well defined, and that allows us to define the square root. So there exists a holomorphic square root on this set, because there exists a log on this set. So we can define it like this. Let's define it as h of z to be e to the 1 over 2 log, and the log depends on this set. If we want to give this a name, let's call this omega hat. So log of omega hat of z. Okay, this is holomorphic, and it is also going to still be a diffeomorphism. This thing is not going to be anything other than injective, because its action is just to half the angle, and the angle function is well defined as we go around this simply connected set. So for every single point there's a well-defined singular valued angle, since it's simply connected. So then this thing is a nicely injective holomorphic function acting on this set. So we can make the further adaptation of considering this set. So consider now this thing, H composed with T of P composed with F. Okay, so what's that going to do? That's going to take this thing and maybe sort of unwrap it to some extent. So let's try and draw a picture of that too. So we still have that 0. I mean, it looks kind of like the first picture, but whatever. This is H of T of P composed with F of our original set. We still have 0 as not part of this, but it's still a simply connected set, still inside the unit disk. Cool. All right, let's call this thing W, just to give it a name. Let's call this thing W. Cool. So let's see what W of 0 does. So W of 0 is H of T of P of F of 0. F of 0 is 0 because it's in that function class. That's this property here. So this is H of T of P of 0. T of P of 0 is just P because T of P just swaps 0 and P. So then this is H of P, actually. So the final thing we want to do is we want to compose this thing with a mapping that sends this guy to 0. So consider the following. So F, let's define F to be this thing. So it's this guy, H of 0, which again is W of 0, composed with H, composed with T of P, composed with F. Okay, then F of 0 is T of H of 0, which is actually the same as W of 0, and this guy is what we define W to be, right? Wherever it is, this is W, right? And then this is this, and therefore it's sending this to 0. So F is a holomorphic mapping, sending 0 to 0. And it is still going to be inside the unit disk because all of these guys send things inside the unit disk to the unit disk, right? So this is a diffeomorphism of the unit disk. So again, we're still in unit disk. So F is actually a guy which is initially defined on our omega tilde up here, and it sends 0 to 0 as well. So F actually belongs to our function class, which is also called F. Okay, let's not call this guy F, let's call this guy pi. So pi belongs to our function class F. Okay, cool. And we can actually try and write little f in terms of pi, just by putting each one of these compositions on the other side. So let's see if we can do that. Let's squeeze it in at the top here, maybe. Okay, so we're going to try and write f in as pi composed with a bunch of other stuff. So we're going to put things on the other side. So let's write pi, and then we'll compose on the left-hand side by t to the minus 1 h of p. So t to the minus 1 h of p, like this. And then we're going to put this h on the other side. So actually, so let g ez squared, like this. And z squared obviously is not injective, but we are not considering this on the entire ball, on the entire disk. After we compose with pi and this guy, then G is actually just going to be restricted to some subset, and on that subset it has to be injective. And I'll talk about this a bit more in a second. So let's just write G for the time being. G is definitely the inverse of the square root, right? And how the square root is defined, whatever set it's defined on, then the inverse of the square root is definitely just c squared. And then we compose with this guy inverse. So t of, right, so we did this, now it's t to the p, the minus 1, like this. So we do this sequence of compositions, and then this thing gives us that f is written in terms of pi, like this. And let's look at this particular mapping here, these first three guys, and let's call that thing phi, like this. Then, what do we have? We have that phi is defined to be equal to t to the p to the minus 1, composed with g, composed with t to the minus 1 of h of p, like this. Cool. And then this thing, just considered as itself, this thing is indeed a mapping of the unit disk to the unit disk, okay? But this is not an injective mapping, because t to the p, this thing is this t to the minus 1 of hp, this thing is the complete diffeomorphism of the disk, right? And then the image is still the disk, and then if we apply it with a square, then we're definitely no longer injective, and then this thing is another diffeomorphism. So this mapping for sure, acting on the entire disk, is non-injective, yeah? But when it's acting on the restriction of pi acting on omega tilde, it will be injective, because at every stage we have injective mappings restricted to our domain. Okay? So, but this guy itself is not, and let's look more closely at this guy. So look, if we do phi of 0, then that is t to the p to the minus 1 of g of h of p minus 1 of 0. Okay, and what do we know about this? We know that t of h of p acting on h of p is actually equal to 0. So then if we put the inverse t on the other side, then t of h of p to the minus 1 of 0 is just going to be h of p. So then this is okay, but h of p is square root, and g is our square, and therefore this thing is just the identity. So then the composition is the identity. So there's t to the p to the minus 1 acting on p, and we know that t of p of 0 is p, so t to the p to the minus 1 of p is actually equal to 0. So this mapping is a diffeomorphism of the disk that maps 0 to 0. Let's try to separate these lines. Yeah, this maps 0 to 0. And therefore we can apply Schwartz, right? So then we can apply Schwartz. We have that z is less than or equal to this, yeah, with equality if and only if it is affine. Right? And in particular, if we take the derivative, then this has got to be less than or equal to, just as a consequence of this, less than or equal to 1. And again, equality if and only if the mapping is affine. But this is not an affine mapping for sure, right? Because these diffeomorphisms, t of p and t of h, definitely are doing things, and for sure g is doing things, it's squaring things. So we actually have to have this is less than 1. This is less than 1, otherwise this is just not true. Yeah? So that means that our mapping f, what we have is that phi composed with pi is equal to f right? And therefore, if we take the derivative, we're going to have that phi prime of pi of 0 is times phi prime of 0 is equal to f prime of 0. And let's look what pi of 0 does. A pi of 0, where is our pi? It's over here. We've already done it. So pi of 0 is actually equal to 0, right? So I need to redo that. So that gives us that I prime of 0, prime of 0 equals f prime of 0. And then if we take the absolute value signs around this, let's not rewrite it, let's just put it here. Okay. But pi is a mapping inside our function space. Yeah? And then this thing is strictly less than 1, right? But obviously this gives us phi prime of 0 is equal to this thing, which should have been the guy that maximizes what this is. So this is this over this, which is strictly bigger than s, because this thing is strictly less than 1. Yeah? Contradiction. So, what does that mean? That means that our initial assumption that it's false, that there exists some p which is outside of our domain, that's wrong. Because if there is such a p, we get to construct this mapping pi, which is inside our function class, such that the derivative of pi at 0 is strictly bigger than the biggest it can possibly be. You know? So, somewhat strangely, if you find the f that maximizes this quantity, and you can find the f by these compactness things we talked about before, then that forces the mapping to be such that the image of omega tilde is the entire unit disk. And pretty weird that it works out that way. So I'm guessing the guys who came up with this were using these diffeomorphisms backwards and forwards and just noticed this kind of identity, that if there was some space which wasn't hit, then they could create something that increases this. And then they said, okay, we can just maximize this, and then we hit the entire space. But yeah, pretty neat and clever proof. All right, so what have we got? We've got a mapping f that takes omega tilde onto the entire disk. I'm going to raise the board, and then I'll just show you why that gives us everything we want. Okay, so we started with omega, which was proper, and simply connected. And we had some Z0 chosen within this guy, okay? And then we found this mapping G, which sends, well, everything's a conformal mapping, this thing into the unit disk, where G of omega is contained within the disk. G of Z0 equals 0. That's what we found. And we found the mapping F, which takes, so this thing was defined to be omega tilde, which takes omega tilde into the disk, and f of the entire thing, omega tilde is the disk, and f of 0 equals 0. Okay, so then finally, I mean, capital F has been used already in the proof, but we don't need it anymore, so let's just define capital F to be the composition of these two guys. Let's first let's do f composed with g. Okay, so then f of omega equals f of g of omega, which is f of omega tilde, which is the entire unit disk. Okay, these are compositions of two conformal mappings. They're still conformal, and we have that capital F of 0 is equal to f of g of 0, not 0, of z0. G of z0, which is f of g of z0 is 0. So it's f of 0, which is 0. So it maps 0 to 0 like this. Yeah? Cool. All right. And that almost does it, except that we also said we want it to be real. We want the derivative to be real. So all we need to do at this point is just compose with a rotation so that the derivative is actually real. So take theta such that e to the I theta f prime z0 is real. Oh, I'm just going to say it's real. Yeah, I mean, I can say it's positive. It's definitely non-zero because it's a conformal mapping. So we can just rotate it so that's on the real line. Yeah. So actually, f is not our final line. F tilde is equal to e to the I theta times f. And then that's it. That'll be our guy. That'll do all the things that we want. Yeah. Cool. That'll do all the things that we want. And it is unique as well. So suppose there exists f1 and f2 that have this property. So what we've got omega mapped onto the unit disk by both f1 and with respect to f2. So the natural thing is to go backwards like this. Let's put this over here. So let's go backwards from the unit disk like this, and then go with f1 back to unit disk. So let's see what happens. So let's take g is equal to f1 composed with f2 to the minus 1. Yeah? Let's see what this mapping does. So it's obviously a diffeomorphism of the unit disk. Yeah? And what else does it do? We know that g of 0 equals f1 of f2 to the minus 1 of 0. So f2 maps z0 onto 0, so the inverse sends this to z0, but then this is sent to this is 1 here. But then this is sent to 0 as well. Yeah? So then this thing is fixing 0. Yeah? This mapping is fixing 0. So we have a diffeomorphism of the disk that fixes 0. Yeah? So by Schwartz, here's a TZ. We have that g of z is less than or equal to this. Okay? But put it over here. g to the minus 1 is also a diffeomorphism that fixes 0. Yeah? So we also have that g to the minus 1 of z is less than or equal to this. Yeah? And these two things together mean that distances have to be preserved, right? Because what? So suppose we have that for some z, this thing is actually strictly less than this, yeah? Then let's do the following. Let's compose with g to the minus 1 on both sides. Then we have z is strictly less than this thing, like this. But we know that this thing has to be less than, strictly less than z. So that we have that z is strictly smaller than z contradiction. So that's impossible. So then we have that g of this thing is equal to this thing. So g is affine by Schwarz. It's actually a rotation. And if we calculate the derivative, so g prime of z is equal to like this, then what? Let's do this at 0, and g prime of 0 is equal to f1 prime of f2 to the minus 1 of 0 and over f2 prime f2 to the minus 1 at 0, right? And f2 sends our initial point z0 to 0, so this is the point z0. And these are both real numbers because that is how we've chosen it. So this thing, they're both non-zero positive real numbers. So this thing is actually a real number bigger than 0. And the only rotation that so should have that g of this thing is just a rotation, so it's e to the I phi of z, and then g prime of z is just this constant function e to the I prime, and therefore, since we know what it is at 0, it's real, so e to the I phi is going to be big and equal to 0, which means that phi is equal to 0, right? Which just means that g of z is just the identity map. Yeah? So if g of z is just the identity map, then that means that z equals f1 composed with f2 to the minus 1, i.e. f1 and f2 are the same thing. Okay? So this condition it means that the conformal mapping we have that does all these things, or this condition that the derivative is such that we insist that it's actually positive real number, means that there is only one such guy. And if we didn't have that, all it would mean would be that any other guy we have is just a rotation of some other guy, right? But if we insist on having that f tilde prime of 0 is a positive real number, then this uniquely defines the Riemann mapping. Okay, so that is the proof of Riemann mapping theorem. Pretty neat, pretty clever. Okay, let's erase the board and talk about Liouville's theorem. Okay, so what Riemann mapping theorem says is that it's a further statement of the fact that there are lots of holomorphic mappings, because it's kind of a surprising thing. I mean, it's a very surprising thing. Given an arbitrary, simply connected domain, we can have a conformal mapping it directly onto the disk, sending any point we want onto 0. That is an amazing amount of flexibility. And yeah, there's lots of applications of this, because the main point about these mappings is that angle preserving. So if you wanted to, map some complicated shape while preserving angles, you can actually do this with a conformal mapping. And there's applications in cartography and whatever, lots of areas. So yeah, a surprising amount of flexibility in the possibilities of constructing conformal mappings. If we consider things in higher dimensions, let's see what happens. So, as we know, a mapping f of z equaling u of xy plus I v of xy, where z equals x plus iy, is holomorphic if and only if it satisfies the Cauchy-Riemann equations. U of x equals v of y, u of y equals minus v of x. No? So, in my complex analysis class, we did this all the time. We said, okay, let's identify this holomorphic mapping with a mapping from R2 to R2. So we find f tilde xy to be the function whose coordinates of u, and then v, like this. No? Then, if we take the derivative, it's a 2 by 2 matrix, so let's take the derivative. I guess there's no return, right? Xy, let's just not do that. What is it? It's the first coordinate, take the first partial. Second coordinate, take the second partial. Second coordinate, first coordinate, take the second partial. Second, take the second. This, yeah? But Cauchy-Riemann equations say that this guy is equal to this guy and this guy is equal to this guy. So we can write everything just in terms of partials with respect to u. So we have u comma x, u comma y. This guy we're going to replace by minus u comma y, and then this guy, it's just going to be u comma x. In other words, it belongs to space of matrices of this form, A minus B, B, A, where A and B are real numbers. Okay? And these guys are what we call the conformal matrices, because they are just rotations times a scaling. So we can just think about this as plus times rotations. Just any rotation multiplied by a positive number is something of this kind. You know? So we can express the Cauchy-Riemann equations as follows, that f is holomorphic is equivalent to the function from R2 to R2 we get from f is such that the gradient belongs to the conformal matrices. Okay. So to try and generalize this to the higher dimensions, I mean, there isn't a natural analog of, well, I mean, there's something called the quaternions, but leaving aside that, in arbitrary dimension, there isn't an analog of the complex numbers. We can't just so easily say something's holomorphic because on some weird field of numbers that happens to be whatever n-dimensional, the natural notion of differentiability is such that we get anything from it. I mean, we don't even have a field. I mean, it's a remarkable thing that we have this two-dimensional field of numbers that behaves just like numbers algebraically. We don't have this for arbitrary dimensions. So there isn't a way to formulate any kind of higher dimensional complex analysis like this by just saying it's calculus with this new number field. However, you might think, okay, why don't I just start with this? Why don't I investigate mappings from Rn to Rn whose differential, which satisfies this differential inclusion that the gradient is such that it's an angle preserving map, because this is ultimately what this says. It says that on a small scale, the thing is angle preserving, right? We just do the higher dimensional version of a tangent line, right? So a T line in whatever n, what do we do? We have that, so given G from omega contained within Rn, going into Rn, then we have that G of x plus h minus G of x, like this. So x is an Rn, h is an Rn, it's a small vector in Rn, right? This thing is approximately equal to times this, where this thing is a matrix in n times n, right? And then there'll be some higher order terms, so the error will be of order h squared, like this, yeah? So if you have your point here, x, yeah, then how can we rewrite this? We can rewrite this as G of this thing is equal to, oops, like this, okay? And this is an affine mapping, right? So we can write it like this if you want. All right, so this is just an affine mapping, and then there's this higher order term. Yeah. So on a small scale, this thing is very, very small, and then what this thing is actually doing, it's just some constant vector that we take away from something that is just linear. In other words, it's an affine mapping. Yeah. So if we have some stuff going on here like these, I mean, I'm drawing it in the plane, so it's hard to do this, but imagine lines coming out in whatever 3 dimensions or n dimensions. Then if we consider the image of these lines, then let's say this guy is Z1 and Z2, yeah, then what do we have? We have that G of Z1 is kind of like the G of Z1 minus x plus this thing, plus, I dropped the error term here, plus the error term, like this, and the same for, actually let's just write let's write k, like this, for k equals 1 to 2, yeah? And in particular, that means that the image, so I should put the G of x0 here. Yeah. So this thing's in the error. We're going to forget about the thing. This is just a point in space, in our n-dimensional space, right? And then this is our vector, take away the initial point, x0, yeah? So then the image of this thing is going to look like what? So we're going to map this to G of x. This point gets mapped to G of x. And then we are going to have that. We're going to take G of x, and then we're going to add this vector dg of x, z x minus x, like this. So by this, I mean this actual point right here. So this vector is z minus x, and this vector here is z2 minus x. Yeah? So we have this vector like this, and we have this vector like this. So let's say that's z1, and that's g. Okay, so in particular, the vectors coming out from this point, g of x, will have the same angle between them because they are acted on by the same thing, the same matrix, which is just a matrix inside the conformal matrices, which is therefore just something that is a rotation times a scaling. So these vectors might be elongated or shrunk, but the angle between them will be preserved, right? Angle between them will be preserved. So if this is the angle theta in whatever n dimensions, then the angle between these vectors is preserved. Yeah. So the differential inclusion into n-dimensional conformal mappings, into n-dimensional conformal matrices will be something that preserves angles. And therefore, it would be natural to think that the analog of a high-dimensional complex analysis would be something where we study mappings into the differential inclusion into n-dimensional conformal mappings. So natural to study mappings into from omega into Rn into Rn with df belongs to this thing. Okay, and it turns out, and most of you have already seen this because I talked about this in the 7,000 level course, that there are not so many of those guys. So let's just briefly state Liouville's theorem and then wrap it up. Liouville from 1851, I think. Suppose F is, I think he did maybe C3, let's say, well, let's just state it for C1 because that's all we need to state it. Okay, now let's be accurate. So C3 from omega into Rn, where omega is a subset of Rn, okay, and gradient belongs to conformal matrices, so it's defined pointways, so it belongs to this everywhere. Then the mapping is Mobius. Then F is Mobius in the following sense. So I'm going to write it down, and then I'm going to explain the pieces. So we are going to have the inversion map, which inverts things through the surface of the sphere. We're going to take some point A, and we invert it, and then we're going to compose it with a reflection, and let's call the reflection Q. And then we're going to compose it with just any affine mapping, which has got a conformal derivative, and then we can just add a constant plus b. Okay, so where, I should write this down, so f of x is equal to this, where a and b are just some vectors in Rn. I of x is this thing, x over mod x squared, and I'll show you in a second that this is inversion for the sphere. Q is affine with the gradient of Q being this guy, so it can be any reflection, but let's just choose one. because no matter what reflection we choose, after we choose it, we are going to rotate it. So any reflection it will work because we're considering reflections composed with any rotation. So it's completely arbitrary that we choose this one, but let's just choose one. So this is our reflection. We're reflecting to the first coordinate. Yeah? So we have, this is our affine mapping Q. We can even set it to be 0 because we don't care about that either, because that's incorporated with this A and B, okay, where Q is this guy, and C is such that gradient of C belongs to conformal matrices, and C is affine. Actually, we just take it to be linear. Let's make it be 0, so F is linear. Because again, full generality is incorporated in this A and B. Okay, so why this? Well, firstly, this thing is inverting things to the surface of the sphere, right? So on the sphere, nothing is changing, right? But the closer you are into 0, the further out this thing sends you. Yeah? And if you think about it, if we do like a smiley face like this, yeah, this guy towards 0 gets mapped further out, and it's kind of not too hard to see that this smiley face is being inverted. Yeah? So this mapping, reflection to the sphere, is a reflection. It's reversing orientation. Yeah? But conformal mappings preserve orientations. So after we compose with this inversion to the sphere, we compose with another reflection so that we get the orientation back. Yeah? So we get the correct orientation. The determinant of this guy at any point will be something which is negative because it's reflecting. Yeah? This thing also has determinant which is negative. So the composition of these guys will be determinant that is positive. Yeah? So that's the point of this Q. And then as I was talking about briefly, this C is just any conformal map. So this just rotates and stretches things. Yeah? So then that means that the reflection is completely arbitrary because any reflection through a plane is any other reflection through another plane after rotate those planes. Yeah? Rotate that plane. Rotate one plane onto the other. So that is this thing. Yeah? And this A and B stuff, well, if we reflect through 0, through a ball centered at 0, that's morally no different than reflecting through a ball centered at A. Yeah? And since we only care about the derivative, then for sure we can just add some constant to f and it's not going to change this condition. Yeah? So what is remarkable about this is that this is just, morally it is just the inversion with a reflection with a change, an affine change of variables. And that's a very, very narrow class of functions, right? There's no point building a theory of a class of functions that satisfy this differential inclusion. You can prove many spectacular theorems because there's basically only one example. So that's not an interesting theory. That's not an interesting theory at all. So there is this massive dichotomy between what happens when you consider the differential inclusion into two-dimensional conformal matrices and what happens when you consider it into high-dimensional conformal matrices. You just don't have a theory. You just can't develop complex analysis of higher dimensions by considering this. It's too strong a condition. And that is actually how geometric function theory starts, because having seen this way back in the day, people understood that there was no higher dimensional theory of this kind, so they wanted to somehow loosen this condition and try and see what analogs of these complex analysis theorems actually did hold true in higher dimensions. And that led to the notion of quasi-conformal, quasi-regular mappings, where these are mappings that don't preserve angles in the pointwise sense that this does, but they also don't mess around angles too much either. And it turns out that there is a rich and powerful theory of such mappings, and those mappings have many applications in other areas. And that is what is typically called geometric function theory. It is the higher dimensional, it is the generalization of complex analysis to higher dimensions, to a more, even in 2 dimensions, to a wider class of functions. And that's what we're going to start talking about in more detail on Monday. Okay, that's it for today. See you guys all on Monday.